Hello, everyone. My name is Daniel Calto. I'm the Global Director of Customer Success Consulting in Elsevier and its academic and government group. Before working for Elsevier, I was Director of Research Strategy at Columbia University and NYU School of Medicine, and my background is primarily at academic medical centers. So my team has broad expertise in the products and services that we sell to the A&G market, including Pure, of course, and we work with our customers to unlock the value of the products and help ensure that they're receiving the maximum value from these solutions. A very important part of our offerings are related to a variety of technologies, which can broadly be termed AI, but we also talk about machine learning, semantic technologies, NLP, et cetera. Oops. I only have about 15 minutes, so I'm going to very quickly move through a streamlined agenda here. I want to first talk about a few of the key implications that are related to the rise in use of AI technologies. I'll try to give you a couple of examples of how these technologies are already being applied in the scholarly communication system and in scientific research more generally. I'll try to use Elsevier products as examples, but of course other companies and providers are also developing similar tools. And finally, I'll touch on some of the limitations and potential dangers of the existing technology and some means to mitigate or minimize those limitations. And if I have time, I'll summarize a brief conclusion and we'll do a little bit of Q&A. So computers have really changed the game for these structured ontologies, extractive AI, semantics, natural language processing, and most recently, generative AI. The combination of large, structured, and curated data sets with rich metadata, together with very fast and powerful computers and the ability, give us the ability to read huge volumes of papers and look for similarities in terms. Once their scholarly record was fully digitized, techniques to expand the power and reach of these capabilities included all the technologies I just mentioned, with generative AI simply being the most recent of those technologies. But before we jump into some examples of these capabilities and how they're, I think, accelerating the research front, I thought we should reflect a little bit on a few of the implications of these technologies, including generative AI. First of all, generative AI inverts search, and search has always been a fundamental core technology driving the internet. We used to type 5 words into a box, get 10,000 results, and read the first 10 of those results. Now we can ask one plain language question and get one narrative answer synthesized from 10 or 100 or 1,000 of the most relevant results. That's a fundamental shift in how we interact with these linked databases, and it's one reason why every major tech company in the world is pouring resources into this right now. Second, there's a clear potential to democratize research results. This is behind the OA principles of opening up the academic literature to lay people. But one barrier to this is that you need a lot of specialized knowledge to read a typical research paper. I was in academic medicine for 10 years, but I couldn't read a genetics paper because I just didn't know enough about genetics. Now I can ask a plain language question and get a plain language answer to that question, and that really has a potential to democratize the world of scientific research with a tool we simply didn't have before. It's early days yet, but we're working on full text generative AI. That's aimed at the academic literature. This could create incredible efficiencies in the way we read literature. One could potentially, for example, summarize 1,000 papers in a single answer, or even better, look for the 5 papers among millions that most clearly answer the question posed. For example, what is the preferred method for gene transfer in a specific strain of transgenic mouse? It's in the literature. It's in those 98 million articles in Scopus. Can we find those 5 papers that treat this most effectively? Now, we tend to think of LLMs as manufacturing text, but the transformer technology that underlines LLMs and makes them possible can really be applied to any pattern recognition activity whatsoever. We can predict pixels in an image. We can predict the next amino acid bases in a DNA sequence. We can predict amino acids in protein folding. We can predict the next line of computer code. We could even predict the next musical notes in a synthetic piece of music. The results are not always coherent for this, but it's important to understand this aspect of generative AI. It's a predictive analytics engine, and it can be applied to anything where you can do predictive analytics. Now, what are the problems? I'm not going to go through these given time, but there's pseudo-authorship. 80% of college undergraduates use generative AI to write papers. 50% of faculty are already using it to help write papers. There's the iteration adjunct problem. If generative AI consumes its own stuff, it quickly turns to nonsense. Hallucinations, the difficulty in ring fencing high quality content, algorithmic bias, data bias that's already in the medical literature, incompetence, the magic trick effects where we anthropomorphize LLM results and think they sound good, so they are accurate, but I won't go into all of those. Let's just look at a couple of capabilities that are really could transform the way we do science. I want to specifically talk about how both extractive and generative AI and these related technologies can be used for research-related purposes. I'm going to skip over Scopus AI, just again given time, but this is powered by a small language model that looks at the words and sentences in your query and assigns them a numerical value based on a language vector space. We point those vectors only at Scopus content. The LLM only comes in at the end to generate the plain language results. But the benefit of this is we always are looking at high quality, curated scientific content, and we annotate that content so you can always see where any specific fact came from. Again, this is what Scopus AI looks like. I don't think there's time to do a demo of it. Another good example, however, of AI is being used to solve a practical problem is the use of AI in chemistry. This gets toward the idea of a forward search. Forward search, again, looks to anticipate the next most likely item in a sequence. This approach is especially relevant for chemists. Comprehensive chemistry databases contain over 15 million known chemical reactions with over 400,000 reaction rules that affect those reactions. That's an enormous amount of data. In pre-computer days, chemists literally needed to imagine a particular pathway to synthesize key compounds. That's one reason why Beilstein, way back in 1880, was trying to index and organize chemical reactions because it was just such a vast set of literature. And like integral calculus, chemical synthesis really relied on a huge amount of implicit knowledge that chemists had. Now, just as LLMs can predict the next word or phrase in a plain language answer, AI-assisted discovery in chemistry can predict the next intermediate product in a synthetic pathway. So more specifically than just predicting reactions, the use of AI in drug discovery is one of the potentially most valuable use cases of all. Again, in the past, drug companies used to have to screen thousands or tens of thousands of small molecules for potential drug targets. Now, with the knowledge of a target receptor or a cell, once that's been prototyped and defined, they may be able to design small molecules much more efficiently using AI to predict the synthesis, lowering costs, and speeding the discovery to drug pipeline. It takes about 18 to 20 years to go from basic experimentation to a saleable drug. If that can be cut in half, that would be an enormous achievement. We could accelerate the basis of pharmaceutical research. Now, I mentioned Beilstein's database that eventually became Reaxys. And Reaxys is a chemistry database that we maintain and offer to our customers. It's got a wide variety of capabilities. Some are standard to any large database, but others are very specifically enabled to assisted by AI. And one of the key uses of this is what we call predictive retrosynthesis. That sounds fancy, but what it entails is knowing what you want your target molecule or chemical substance to be, and then working backwards to all the precursors in of the compound. There are almost always multiple routes to create a compound, and most of these have multiple steps. Now, a chemist can now use AI-assisted pattern matching to map out the multiple routes to a compound. You're essentially working backward from the compound you want to the precursors of the compound and all the intermediate steps. He or she can decide which of the many pathways is best for their purposes, which is the cheapest pathway, which is the fastest pathway, which is the least toxic pathway. All of this can be determined, again, using AI-assisted retrosynthesis, and this is already working. This has been working for 2 or 3 years. So the use of the AI in the life sciences is among the most promising avenues that we see. It's applying both extractive and generative AI techniques to make things faster and easier for researchers in the life sciences. So given some of these use cases and the promise of these use cases, why aren't we already living in this frictionless world where we have faster and better information capture, retrieval, summarization? Well, because there's still significant challenges to these technologies. The more mature technologies, the more safeguards have been developed to channel their capabilities and minimize their flaws. So we have pretty good ways of dealing with extractive AI, dealing with semantic technologies, and natural language processing. I think we still have a lot to figure out about generative AI. There are a lot of data quality and completeness issues. It only works if you have high data quality. This includes the biases embedded in the data itself. For example, until recently, most pharma testing was done on men in Western countries. Now that's better recognized, it's more mitigated in drug studies, but it's still embedded in the original data. Another source of potential bias is the algorithm itself. If the algorithm is not written properly, it may miss important results or outlier results that may be of importance. Sometimes generative AI content is just not that good. It's not as good as a human who really knows what they're doing. Hallucinations are primarily a problem of LLMs and not a problem for some of these technologies that is shown, but there's still a serious problem and question whenever accuracy is paramount. For example, in biomedical research, even a 5% inaccurate rate is very, very serious. You're treating people often with life and death conditions. We also have problems with people, the speed of technological development, the fact that LLMs and generative AI generally are a complete black box. It's hard to find people who even understand how the algorithms work, and even if they understand the algorithms, they don't necessarily understand why the LLM is answering in the way it does. That's problematic, particularly when you think of science and you think the need for transparency and the ability to drill down to the original article. So when we design these systems, it's extremely important that we keep all these things in mind if we're going to use these technologies effectively and not get caught in a rabbit hole or get caught in something that pollutes the scientific record and the scholarly communications data instead of enhancing it. Again, I don't want to go into mitigating all these risks because we don't have time to do that. But one of the best strategies that the technologists have come up with is to stack relevant technologies. We stack data sets, we stack processes together, we design specific ways to use these technologies so that we're minimizing the risk of hallucination. We're minimizing the risk of low quality information bleeding into the answer. And that we always have the ability to drill down and look at the underlying data that's driving the answer. When Scopus AI answers plain language questions, for example, the results themselves, as I said, are strictly drawn from the academic literature. They're not drawn from the flotsam and jetsam on the internet, general things that have been written. And when Scopus AI doesn't have enough to give a coherent answer, it says, I don't have enough information to yield an answer. So that's a very simple technique, but we're saying if you put together a malformed query or a query that Scopus AI simply can't answer because it's not in the literature or the answer is too contradictory, it will tell you, I don't have enough information to answer. These kind of simple safeguards can make a big difference in the way we use these technologies. Whoops, what happened? There we go. I want to end it here. Generative AI and even extractive AI are a major area of technological development currently. It has huge potential to impact how research is done, how it's disseminated, and even who has a chance to do research around the world. As such, the focus around the technology, I think, is well warranted. There's a lot of hype around generative AI. There's some ideas that it's going to change everything in 3 years. I don't think that's the case. We still need humans to do research. I think that's going to continue. But it's important to remember also that these technologies, most of them are not new. We've been structuring information for hundreds of years. The Lancet was first published in 1823. The Royal Society published Philosophical Transactions back in 1665. It's still a journal that's published to this day. So the computer revolution and the subsequent vast increases in speed and the vast drops in the cost of computing have allowed for the substantial acceleration of these technologies, structured vocabularies, databases, and extractive and generative AI. These vast data stores have encouraged the growth of these technologies, and they're still in use today. Generative AI is the most recent of these. It has a magic trick effect. But the key to harnessing these technologies is the careful architecting of fit-for-purpose data, technologies, and safeguards. I want to thank you all for your attendance. We've got some coffee waiting outside, and I'll be around for the rest of the conference if you want to follow up on any of this. I'm also happy to field any of your questions or comments, and thank you again for your time and attention. I'm happy to answer any questions or take any comments that you might have.
Thank you very much, Daniel.